Okay, we are now aware of the concepts that are associated with 1D flow, okay, 1D seepage. Those concepts are used to determine the hydraulic conductivity of a soil in the lab. Okay? We're going to use these concepts now to describe flow in two dimensions. Flow in two dimensions, or seepage in 2D, is the most common case in the field, where we have a civil engineering structure, for example, like a dam, okay, or flow to a drain, etc. This is the common case, and therefore this is why we have this lecture series. In this slide we have a comparison between 1D flow and 2D flow, basically the difference between them. In 1D flow, the velocity vectors are parallel. Okay, so if we think of a cylinder of soil in the lab, subjected to a Darcy type experiment, if we were to find the velocity of the fluid at any point and describe it by a vector for each point, then we would draw parallel vectors, and in fact they would be essentially of the same size, because the flow velocity doesn't vary across the specimen, provided that the specimen is made up of just one soil, which is the case typically when we want to determine the hydraulic conductivity. Now, in the case of 2D flow, the velocity vectors are not necessarily parallel, okay? And they're actually confined to a single plane, as we will see when we talk about this example here. This drawing shows a, let me zoom in a little bit. This drawing shows a profile, okay? It's a special profile where we have the soil, mass, rock here, here's the ground surface, but above the ground surface there is a water table on one side and a water table on the opposite side of a wall that is embedded in the soil a certain amount and protrudes out of the soil a certain amount. This wall is basically runs into the page. Okay, so you can think of the wall like this, running into the page and out. Okay? Now, in this case, the wall is actually separating two reservoirs, as we said. This reservoir is at an elevation, the top of it, the surface of it is at an elevation that is higher than the elevation of this reservoir. So you can imagine that a point here versus a point here, these 2 points have different head. Okay, therefore you can expect that flow will occur from this point to this point. Now the flow is not going to occur or happen like this, okay, from this point to this point in a horizontal manner. The flow is going to reflect what the geometry of the system is. Okay, so let's consider a point here where we monitor, or we begin to monitor, the trajectory or path of our water droplet. So let's say that there's a water droplet at this point and we monitor its path. Clearly this water point or drop wants to eventually make it to this side. So what it's going to do, it's going to go along this so-called flow line and eventually end up here. Okay? Now, as you can see, the vectors that are shown here along the flow line, they should be right on top of the flow line actually. They are not parallel, right? This one is like this one is like that. These two lines cross, therefore these two vectors are not parallel. Okay? So, this is the case of 2D flow. Velocity vectors are not necessarily, in this case they're not, parallel. Okay? Now what we have said here, or implied here, is that the flow will occur through the soil. Clearly that's the intent of what we're trying to describe. Flow through soil, that is seepage, right? Now, even though rock has a permeability or a hydraulic conductivity, it has a very low hydraulic conductivity. So what we assume is that the flow will be confined to the soil layer above the bedrock. we assume that the flow or the fluid doesn't flow through the rock, even though it actually may, but it does so very, very slowly, therefore we can neglect that flow. The flow is going to be concentrated or confined in the soil mass. Okay? Clearly, if there is a hole in the wall, then the water is going to flow through that hole like that. But we assume that our systems are built correctly or efficiently so that we don't have those types of problems. Now, the situation that you see here is actually a common situation in the field. And this is the case where we want to remove, let's say we have some kind of lake, okay, or reservoir, and we want to work close to the ground surface in a location. So what we do is we place a wall, okay, in this case we actually insert a wall that is already prefabricated. We can talk about that later on when we take foundations course, okay. But essentially what we do is place a wall and then we place a pump to remove the water from this location so that we can bring crew in here and work, etc., or equipment. Now, as you can imagine, the type of pump that you are going to design or select for this operation depends on how much water comes in here per unit time. That is, what is the flow rate expected at this location? What is the flow rate expected at this location? So, knowing the Q coming into this area, you can then select the appropriate pump so that you can remove enough water to be able to have the equipment or whatever the people here working. Now, it is important to, of course, realize that that Q depends on the hydraulic conductivity of this soil. So you can imagine that if this soil is clay, for example, that has a very low K, low hydraulic conductivity, then the water is going to have a hard time going through, and therefore you will get very little water per unit time, that is a very low flow rate, into this area or location. In which case you may need just a small pump. Okay. Now, if this is sand or gravel, let's say, for the extreme case, let's say that this is gravel with a very high hydraulic conductivity, you can expect the water coming in here, the flow rate of that water to be very high. Therefore, you would have to select or buy or rent, whatever, a very large pump. So, for engineering in this location, we need to know how much water per unit time, Q, will come into this location so that we can actually select the pump to remove the water constantly as it comes in. Okay, that is an example of why we need to understand 2D flow. Of course, to describe flow or any engineering system, we need mathematics and physics. So what we're going to do is we're going to take this little element, this little red square here, basically denotes an element or a point. Okay, remember, element and point are the same thing. Okay, we take a point which we draw as an element because that way we can see it. Okay, and we're going to remove it from this figure, I guess, and then we're going to zoom in and look at what happens in terms of flow across this element. Clearly, if you have a point that water droplet that begins its trajectory at this point, it may actually go like this, right? This would be the flow line associated to that trajectory. So it would pass through that point. Okay, so we're going to use that point to be able to derive the equation that describes 2D flow. Okay, here's our point. We're going to write out our axes. We know that the horizontal axis is x and the vertical axis pointing downwards for positive is z. Okay, you've seen this before. You have seen this before. Okay, that's z. So that means y is in this direction. Okay, now here's our point, but we have zoomed the point so that we can see it better and put dimensions on it. this dimension is dx. Okay, what is that? That is an infinitesimal dimension, right? We use calculus to size things that have no size. Okay, that's what calculus does. So we use this calculus dimension dx. We use this calculus dimension dz for this length, okay, of the point. And we're going to say that the length of the point into the page is L. Okay, so this is like a 3D version of the point, or 3D view of the point. All right. Now, let's look at the velocities. If we look at this slide right here, you can see that the flow line, the trajectory, is passing through the point, right? At some kind of an angle like this, right? So we can think of this vector as being the velocity vector for that point. The point meaning this element, because we know that an element is a point, right? And so what we can do is we can decompose this vector into its components in the x direction and in the z direction. That way we can describe the flow with respect to velocity with two components, the component in the z direction and the component in the x direction. Okay, now let's think of the component in the x direction. The velocity of the fluid as it enters this point is Vx, that is in the x direction. X component of that vector that we drew here. Okay? The velocity of the fluid coming out of the point may be different. Okay? So we write it out as the initial velocity, that is the velocity coming in, plus any change in velocity. Okay? This change in velocity is written as a rate of change in velocity. Okay. In the z direction, the velocity of the fluid coming into the point is Vz, and the velocity of the fluid as it exits the point is Vz, the entrance velocity, plus the rate of change in the velocity in that direction. Partial Vz, partial z dz. Same thing applies over here. Now you may ask, hold on one second, I thought in is the same as out. That is the case for flow rate, if of course we have met certain assumptions, and we will get to that. The point here is that the velocity changes throughout the flow. Okay? So, or throughout the trajectory. So let's look at the flow line here. This one here, for example. The fluid droplet that we are trying to monitor here, it may actually flow slowly, and then, initially, then in the curve here, it may actually accelerate, okay? So the velocity will be higher, and then it may actually slow down. So the velocity along a flow line is not necessarily the same, okay? Because it's not necessarily the same, then at any point the velocity can change, which is what we are trying to show here. The velocity coming in may not be the same as that coming out, but for certain assumptions, the flow rate in is equal to the flow rate out, and those are the assumptions that we're going to use here. So you will see this as we derive the equation that we need based on these parameters here to describe the flow. And here it is. So this is the derivation of that equation. We're going to basically reveal the name at the end, although you may already know what the equation's name is. But we're going to derive the equation that we need to describe 2D flow. Okay? Now, essentially what we're going to use is continuity, Q in equal to Q out, or conservation of mass. So what we have to remember when we go through this derivation is that in the z direction, the area cross-sectional area of flow is this, right? Which is L times dx. In the z direction, sorry, in the x direction, this is in the z direction, right? In the x direction, the flow cross-sectional area, is L dz. So this is z, L dz, right? This is here. So this is a cross-sectional area of flow for the fluid that component that flows in the x direction, and this is the cross-sectional area of flow for the fluid that flows in the z direction. Components, right? Remember that we are using components to describe the vector, just like you would use, for any other engineering type of problem or physics problem. Okay, so let's begin with the derivation. Q in. What is the flow rate coming into the point or the element? Same. Point and element are the same. Well, Q is equal to velocity times area. We already defined the area, right? The areas. So, in the x direction, the velocity of the fluid coming in is Vx, and the cross-sectional area, as we described before, is dzL. In the z direction, the velocity of the fluid coming in is Vz, and the area associated with that velocity is dxL. Now, Q out. Q out is associated to the velocities coming out. Okay? So in the x direction, the velocity of the fluid coming out of the point or element is given by this term here, which is this term. The area is dzL, just like up here, the cross-sectional area flow. Okay? Now in the z direction, the velocity of the fluid coming out of the point is given by this term, which is this term, and the area is dxL, as shown here as well. Okay? Q in, Q out. Now, we make two assumptions here. The first one is that the point is not changing in size, okay, during flow. That means that the soil cannot be deforming during flow, okay, or deforming significantly, let's say. So the element is of constant volume. That's what that means, or that's what that says here. And we also assume that water is incompressible. Now, water is not truly incompressible. Incompressibility means that the stiffness is infinity, which is impossible for a material, right? So water is not incompressible. Water is compressible, but it has such a high stiffness compared to other materials that we assume sometimes for it to be incompressible, okay? So make sure that you remember that, because some people tend to believe that water is actually incompressible, which is impossible, okay? Now, with these assumptions, then we can say, look, Q in is equal to Q out, which is to say Q in minus Q out, we move this one to this side, is equal to 0. So now, we're going to use this equation here. We're going to write this equation out, but with these terms up here, with these terms. Okay? So let's begin. Vx dzL plus Vz dxL This is Q in right here. And these 4 terms, 1, 2, 3, 4, are Q out. Notice that the Q out terms have a minus. Okay, because the minus is here. So, Vx dCl minus dVx dx dx dZl, okay, etc., etc. Now, let's look at these first 2 terms. I'm going to drop this down a little bit. Okay. Essentially what I've done here is I basically expanded this. So Vx dZl, okay, and then dVx dx dx dZl, because you have to multiply this one times this one and this one times this one. So this one times this one is dVx dx dx dZl. Okay. Same thing goes for this one. This is expanded into 2. That times that plus that times that, which over here means that it's minus that minus that. Okay. And that is all the summation here is equal to 0. By summation, I mean that there are also negative, terms that are summed. Okay. Okay. Now, once we have written everything out, realize that some of the terms are repeated. So Vx dCl minus Vx dCl. So this one goes with this one. Vz dxl, Vz dxl. That one goes with that one. And we are left with this term and this term. So minus that equals 0. Which is to say, minus this equal this, because we can move this negative, this minus or negative quantity to the other side, it becomes positive. Okay? So we are left with this. Now, if we divide both sides by L, then L cancels. If we divide both sides by dz, dz cancels. If we divide both sides by dx, right, dx cancels. So we are left with minus dvx dx is equal to dvz dz, which is to say 0 is equal to dvz dz plus dvx dx. Okay? So far so good, we keep going. Okay, now we're going to invoke Darcy's law. Remember 1D flow? The 1D flow equation? We're going to invoke it. Basically we have Darcy's law is equal to Q is equal to KIA, right? But if we divide by A, we get the Darcy velocity, which is equal to Ki. Darcy velocity is equal to Ki, right here. Now, we're going to write it out in the 2 components. The Darcy velocity in the x direction is the permeability, or sorry, hydraulic conductivity in the x direction times the gradient in the x direction. And the Darcy velocity in the z direction is the hydraulic conductivity in the z direction times the gradient in the z direction. Okay, we just written out Darcy's law in terms of the Darcy velocity and using the components. Okay, now here we can expand further. We can say, look, Darcy velocity in the x direction is the hydraulic conductivity in the x direction times the gradient in the x direction, which is the change in head divided by the change in length. Okay, but in the calculus format. Change in h over change in length of which the length over which the head is lost. Okay, so we can write it in calculus format. Delta h over delta x. Here the same, but here we have delta h over delta c for the c component. Now we're going to take this equation here, which describes basically our Q in equal to Q out. Remember, Q in equal to Q out. All this stuff leads to this equation. Sorry, all this stuff here leads to this equation right here. Okay, so we're going to take that equation we're going to put it right here, the same, just rewritten, okay, and then we're going to write it out with Darcy's law. So dVz dz becomes d Vz dz. This should be a partial right here. Please correct it in your document. These are partials. Okay? So this right here is Vz. Sorry, Vx. Or sorry, Vz. This is Vc right here. Vc, Vz, Vz. Okay, and then here, Vx, partial of x. Combining this with the into and placing this in here so we can get that. Okay? Keep going. If we assume that the K's are the same, that is, the hydraulic conductivity in the x direction is the same as in the z direction, which is an appropriate assumption for most soils. Sometimes clay soils do not feature this equality, okay? But we can assume for now that they do. All soils do. Let's say we can assume. In that case, we can write this equation like this. Why? Because the K's, if they are the same, we can remove them. We can divide the whole equation, 0 is equal to that, by the K, which in this case would be the same, Kz equal to Kx equal to K, right? And those terms would be removed, and we are left with partial H, partial C over partial Z, plus partial H, partial X over partial X, in which case we can rewrite that equation which I just dictated there with squares. Okay? So we get this equation right here. Partial squared H over partial X squared plus partial squared H over partial Z squared equal to 0. This is Laplace's equation in 2 dimensions, where the term that is associated with the Laplace's equation is the head. Okay, remember that head is the unit or the term that we use for energy, even though head doesn't have units of energy, it has units of distance. Okay? This equation is a very important equation. Now, it is very important to also state here that Laplace was not necessarily interested in fluid flow through soil. He was interested in describing the flow of energy, of any sort of energy, through a material. Okay? So if you were to actually remove this H and write a big T, then what you would get is an equation that describes the flow of temperature through a material, for example. Okay? In this case, we have used Darcy's law, we have used flow concepts, therefore we arrive at a Laplace's equation that is used to describe flow into the flow of fluid through soil. Okay, so Laplace's equation, as we've said, it represents the energy loss or flow through any resistive medium. Okay, any medium that resists that flow of energy. In which case, in our case, I guess, the resistance is provided by the grains, right? As the fluid drags along the grains, and therefore the resistance term is the permeability or hydraulic conductivity. Remember that for our derivation we assumed that the Darcy equation was valid, Darcy's law, we assume that the element was of constant volume. We assume that the hydraulic conductivity was the same in both directions of relevance, and we also assume that the soil was just one type of soil, so the hydraulic conductivity is the same throughout the soil mass. Something that we didn't mention, but is clearly part of this derivation, is that the degree of saturation is 1 or 100%. Okay? That means that the soil is completely saturated. If the soil is not completely saturated, then we have additional terms, and the Laplace equation, or the Laplace's equation that we get, wouldn't be this one. It would be one that is more complex, because it involves the flow of air as well as water. Okay. So here's Laplace's equation rewritten in a nicer form because it's printed out by the computer. Okay. Now, over here as a title of this slide, we have that the main point is to get the flow rate. And this is basically not necessarily the main point. The main point is to understand how to describe 2D flow. But as we said earlier, it is important to realize that when we use these type of concepts, we use them for engineering. And one example is to get the flow rate into a location or into an excavation, for example, so that we can select the appropriate systems to keep the water out. This is one example, okay? It's also important to realize that when we design dams, this equation is probably the most important equation. And this is because when we design a dam, we would like the water to be retained by the soil that constitutes the dam, right? And so we need to make sure that the flow through the dam is such that there is a reservoir that is maintained behind the dam, right? Nobody wants to build a dam that, once finished, the flow rate through the dam is so large that the dam doesn't really retain any water. Okay, of course. So examples: dam engineering, Laplace; excavations, pump selection, Laplace. Okay. Now, at this point, you may ask, well, here's a problem, or here's a situation in the field, and I would like to describe this 2D flow. Okay, and now I have this equation. So how do I use this equation to describe the flow here? There's no flow rate, there's no Q. In fact, how can I use this equation to describe the flow here versus in another problem? Okay? And that is a very valid question. To answer it, we need to think about what this equation is. Okay? What type of equation it is. What is it? This is a second order differential equation, right? Second order because we have the squared here, right? Now, let's say that we remember our mathematics, DFQs, and we solve it. So what will we get? When you solve a partial differential equation, in this case of the second order, what do you get? Do you get a number? Do you get, an answer? 3.5, 7, whatever? Or what is it that you get? Well, if you remember correctly, what you get is an equation. So the solution to a differential equation, like this one, for example, is an algebraic equation. Another equation, right? And what is the solution? What do you think the solution to this equation looks like? Not the form, but what are the parameters? Well, the solution is the head as a function of x and z. So the solution to this equation is another equation that looks like this. Okay? H is equal to some function of x and z. So if you have this equation, then essentially what you can get is the head, that is the total head, there's no subscript, that means total, the total head at any point. Why at any point? Because a point here, for example, a point here is described by its coordinates, x, z. So the coordinates of this point, depending on the location of the origin, let's say this is the origin, 50, 10. 50, x equal to 50, z equal to 10. So if we have this equation, if we know that this is 50 and this is 10, then we can get h. Okay? So for example, if the function is x plus z, h is equal to, let's say for a given problem, h is equal to x plus z. Let's say that's the solution to the equation that we get. Solution to the differential equation, Laplace. We get this. Then for this point that we just talked about, x equal to 50, z comma 10, 50 plus 10, 60. That means that the head at that point is 60. Okay, now how does that help us? This helps us because if we know the head at a point and the head at another point, then we can describe the flow from that point to the other. Now, you may still be thinking, well, how do I get from this equation to this one, for example? How do I know that the equation is not h is equal to x squared plus z over x or something like that? Well, that depends on the problem. Here's one problem. That's one example with one wall. What happens if you have 3 walls? 1, 2, 3. Or what happens if you have a dam? What happens if you have a different geometry? In that case, the solution to the equation will be different. And here's where we can now go back again to differential equations and remember that to solve an equation like this, you need more information. You need what are called the boundary conditions or initial conditions. Remember that? Well, boundary conditions, which are the ones used in this case, are conditions at boundaries. That's all it is. So when we go to the problem, that is our example here, what we need to do first, before we solve the equation, is to figure out if we know any information at boundaries. So what are the boundaries? Well, here's a boundary. Do we know anything about the head at this boundary? Well, a point here is located at the boundary, right? So we know that the pressure head is that distance, and the elevation head is this distance. So we know the total head at any point along this boundary. That is a boundary condition. So we can use that boundary condition to solve the equation. What about on this side? Yes, along this boundary, the pressure head is this little distance here, and the elevation head is that distance. Of course, we have assumed that the datum is this. Okay? So, it's interesting for most students. When I was a student, it was interesting to me to realize that to solve a differential equation, we had to use these so-called boundary conditions. And when we were taking mathematics classes, we really didn't know what that meant. It was all math. But boundary conditions, the word boundary comes from boundaries of the problem. Okay, that's cool, I think. Okay, so here's our equation. We need to know what type of problem we have so that we can prescribe and identify and prescribe our boundary conditions so that then we can solve the equation with those boundary conditions and get to the equation that we desire. Okay, here are two examples, but we are going to get a different equation for all different problems that we solve. Okay, once we know what the solution is, then we can determine the head at any point, knowing the location or coordinates of that point. Now, you may be thinking, oh my god, I'm going to have to go back and learn diffqs again and solve this equation with boundary conditions and all this, and integration and all that, separation of variables and all that, right? But perhaps you already have seen the slides that come next, and you don't see any of that. So what we have done as engineers is we have simplified the situation by using a graphical form or graphical method called flow nets to solve the equations. Sorry, the equation. Okay? Now you may say, well, if we use a graphical form, maybe we're going to get, a lower accuracy or something. It's better to use pure math. Well, yes, it's probably going to be better to use pure math because the accuracy would be basically 100%. But it's much easier and actually more efficient in terms of how we can visualize the problem to use the graphical procedure. Now I should say here, and as you have read in the book, that the graphical procedure, the flow nets procedure, it is a solution of the Laplace's equation. It's not an estimation or an approximate way of getting what the mathematics would give you. It is actually solving the equation in a graphical format. Okay, so these two are the same. However, the graphical procedure requires that you draw what is the so-called flow net. And in drawing, one may make, some little errors, etc. If you do not make these errors, then you would get the same answer using math as using the flow nets or graphical procedure, because the graphical procedure is itself a solution to the equation. Okay, and that will be the topic of the next